Have you ever wondered what endianness means in computing? Maybe you've heard little-endian and big-endian bandied around, but you're not sure what they mean or if they even matter. In this video, I'll not only explain endianness in a way that makes sense, so no eggs or Gulliver's Travels here, but I'll also show you how to handle it in C and C++. So we'll start with the basics. What endianness is, why it exists, why we've ended up with systems with different endianness in the first place, and why most programmers rarely need to worry about it anyway. And then after that, I'll give you 4 different ways to convert between little-endian and big-endian and vice versa in C and C++, starting with the easiest to understand and finishing with the fastest. And then finally, I'll share a common pitfall that you'll want to avoid, and also best practices for writing portable endianness-safe code. Sounds good? Let's get started. So what is endianness? It's all about how large numbers are stored in memory. So let's first have a look at the way we write numbers as humans. So take number 12,345. We start with the largest digit, the 10,000, and we write it from left to right. So 1, 2, 3, 4, 5. This is, without you knowing it, a big-endian format because we start with the largest, the biggest or most significant digit first, and then write it down to the smallest. However, theoretically, we could also write it the other way around, starting with the least significant digits, so the 5, and then writing it in increasing order, so 5, 4, 3, 2, 1. Confusing? That's only because you're so used to writing numbers in big-endian format that anything else looks weird. If everybody decided or agreed to write numbers in little-endian format, then that would be the norm, and it would be big-endian that you would find confusing or weird. Now, in the computing world, we do have CPUs that are big-endian and CPUs that are little-endian. Heck, we even have CPUs that are considered bi-endian, so they can do both. Why? Why on earth do we have to put up with this in the first place? Well, back in the 60s and 70s, so ancient times as far as computing is concerned, there were very few standards, so things weren't standardized, and you had multiple companies vying with each other for global dominance. They were competing against each other. And as any good entrepreneur knows, you need to differentiate yourself from the competition. So if one company did things one way, then other companies would do things the other way in order to differentiate themselves from each other. And then they would explain why their approach was better than their competitors, whether it's true or not. So Intel went little-endian with their x86 CPUs, which ended up in PCs, while companies like Motorola went for big-endian, which they used in their 68,000 series, which ended up in the original Macintosh computers and Commodore Amiga. Let's take a closer look at how this is done in computers. So with computers, numbers are stored in a binary format. So ones and zeros organized with the basic unit being 1 byte. So 1 byte is 8 bits. And with 1 byte, you can store any number between 0 and 255, or if you're doing signed numbers, minus 128 and 127. You can also represent all the letters of the alphabet more using ASCII coding with 1 byte per character. And everything's fine so long as you stay within those narrow ranges. But of course, we have much larger numbers. So what happens when you need to represent large numbers? Obviously, you're going to have to use multiple bytes to store it. So if you add an extra byte, you get 2 bytes, 16-bit number. You can represent any number from 0 to 65,535. Double it again to 4 bytes, so 32 bits. And you can go up to just over 4 billion. And if you double it again to 8 bytes or 64-bit, which is what modern computers tend to use, then you can store insanely large numbers. And here's where endianness comes into play. In what order do we store those bytes in memory? Let's take the number 324,508,639. So this in hexadecimal format is 13579BDF. And we're using hexadecimal because 2 hexadecimal digits fits cleanly into a byte. So we can separate this out into 4 bytes already. In the big-endian system, we start with the most significant byte, so the large end of the number, and we store that first in memory, and then next come the lesser significant digits. So 1357 9B DF. That is our number stored in big-endian format. With little-endian systems, we swap things around, the other way around. So we start with the least significant byte, which comes first, and then we go in ascending order. So we end up with DF, 9B, 57, 13. And both of them represent the same number, just using a different endianness. And that, in an eggshell, is endianness. It's simply the order that the bytes of large numbers get stored in memory. By the way, the name endianness does come from, or was inspired by Jonathan Swift's classic novel Gulliver's Travels, in which Lilliput and Blefuscu were two kingdoms that had a war over whether eggs should be eaten from the little end or the big end. So little enders, big enders, little-endian, big-endian, you get it? Anyway, be grateful that the big companies only competed on the byte order, because they could also have gone big-endian and little-endian on the order of the bits within a byte, in which case there would be 4 possible different combinations and it would make our brains seriously hurt. While this is all very interesting, as a programmer, you're unlikely to have to worry about it most of the time. So the CPU reads and writes numbers in whatever its native endian format is, and it does this automatically. So long as your code doesn't need to interact with data from a system using different endianness, then everything is in the same endian format and it all just works. You only need to worry about endianness in specific circumstances. So the first one being transferring data between computer hardware of different endianness. And that can include transferring data between the CPU and a peripheral. For example, my Amiga OS graphics drivers have to interface a big-endian PowerPC CPU with a little-endian GPU. So the data needs to be converted of endianness, but when transferring it in either direction. Second situation is transferring data between computers, even if they're both little-endian, because the TCP/IP network protocol has decided to go with big-endian for addressing. And finally, loading and saving of data to or from disk, when the data format is in a different endianness of the CPU. Oh, and there's one more. When you're looking at memory in a debugger on a little-endian system, and that's because you look at the memory as a big array, and the numbers in the memory will be stored in little-endian format, so you have to mentally do the swapping. This is one case situation where the computer can't do the endianness swapping for you automatically, because in order to do the endianness swapping correctly, you need to know how big the number is. So let's take our number again, the number we used before. The little-endian number DF9B5713. If you want to convert that to big-endian correctly, we need to know that it's a 4-byte number. So if you swap it as a 32-bit 4-byte number, then it becomes 1357 9B DF, which is correct. Now, if you treat it as two 16-bit numbers, then you get a totally different number. If you still find endianness confusing, then I have some great news for you. Endianness is likely to become less and less important because little-endian format CPUs are now dominant, like so dominant that Linux for PowerPC is switching to little-endian. So PowerPC is one of the CPUs that can handle both big and little-endian, but maintaining drivers for big-endian CPUs in an increasingly little-endian computing world was just getting too heavy, and I know all about that because I have to deal with it when writing Amiga OS graphics drivers. So the easiest solution was to switch the endianness that the CPU uses by default to match the attached hardware. So now you understand endianness, but how do you convert between little and big-endian or vice versa when you actually need to do it? I'm going to show you 4 ways to convert between big-endian and little-endian and vice versa, starting with the slowest because that also happens to be the easiest one to understand. Keep watching to the end because I'm also going to reveal a gotcha that can really trip you up and give you best practices on how to write endianness handling code that will work on any CPU. So the most obvious way to do endianness conversion is to physically shift each of the individual bytes. So for example, here I've got a function that byte swaps a 32-bit word, and it's done like this. You take the value and you AND it with a bit mask to isolate one of the bytes, like this. And then you either right shift or left shift that byte to the right location. So in this case, this first byte gets shifted to the right by 24 bits. And then finally, you OR all the individual bytes back together again to form the byte swapped 32-bit number. And that certainly works. If you look at here, we've got a 16-bit endian swap. So 0123 becomes 2301, and then 32-bit swap, 64-bit swap. The 64-bit byte swap code looks a little bit ugly. And this works on every single CPU, regardless of endianness, but it's rather slow. It's like here with the 32 bits, just to byte swap a 32-bit word, we've got 1, 2, 3, 6, 9, 11 instructions. And most modern CPUs have built-in byte swapping instructions that can do it in one go. Theoretically, if the compiler's optimizer figures out what you're doing with this, figures out what this means, that it could optimize it away to the byte swapping instruction. However, don't count on it. Now, so obviously for speed, we'd want to use the CPU's built-in byte swapping instructions. Now, we could do that by inserting assembly code into our C code. However, then we'd have to write assembly code for every single CPU architecture that we want to support. And not only that, the way you insert assembly inline into C code varies on a compiler-to-compiler basis. Fortunately, though, most compilers have these built-in functions. So if you're using Visual Studio, MSVC, then you've got these byte swap, ushort, ulong, uint64. And if you're using GCC, or I believe Clang has it as well, Clang, then you've got these built-in _b swaps 16, 32, and 64. And using those built-in functions should be mapped to the optimal instructions for each CPU. So without having to resort to assembly, you get the optimal high-performance endianness swapping code. And this is where we get to our first gotcha. So if you look down here, everything is fine with endian swapping or byte swapping integers. And then we get to a floating point number. This is 1.1. This is the value, the way it is in the bits, bitwise, in hex format. And if we do a swap endian 32, then, oh, that is nothing like what the byte swap version of this should be. So what's happened is you start with a floating point number, and then you pass it to a function that takes an integer. So C and C++ will implicitly cast or convert that float to an integer. So in this case, 1.1 gets converted to 1. And then it byte swaps that value. So in this case, we end up with a byte swap version of 1, which is obviously not what we want. Instead, what we need is something called a bit cast. So that means you take the float and you convert it to an integer without doing any actual conversion. So you just take the bits and say, well, let's pretend that instead of this being a float, it's an integer. If you're using C++ 20, so C++ year 2020 or newer, then they have a bit cast built in. However, that's not available on C and not available on older versions of C++. So in that case, you need to pull a little trick with a union. So this union has a float and a 32-bit integer. You write to it as a float and you read it as an integer. And that will work on all compilers. And you can also do that with 64-bit floats or doubles. Same thing. There is another method that you can use that uses pointer trickery, but let's not get into that. This works. If you use that, you look down here, we've used our swap endian 32F, and it is doing the byte swapping correctly because we don't have that implicit conversion from float to integer. Okay, the third method of doing endianness conversion is to use the conversion functions built into the networking stack. So a lot of people don't know this, but the TCP/IP protocol that powers the internet is big-endian. So things like the IP address is stored in big-endian format, which means that it needs to be converted on little-endian CPUs. And to do that, the networking stack has provided some convenient little functions or macros like h2ns, which converts a 16-bit number. That means short integer. There's h2nl, and on Windows, you've also got h2nll for 64-bit numbers. And likewise, you've got the inverse saying so n is network byte order to h, which is host CPU byte order. So you've got h2ns and N to HS, and so on and so forth. And these are convenient functions that allow you to convert things like IP addresses to network byte order on any machine. Now, there is one problem with these functions, and that is that they only convert endianness on little-endian machines, because on big-endian machines already store numbers in big-endians, so they do not need IP addresses, for example, do not need to be converted to network byte order because it's already in the right order. This is not a mistake. They're doing exactly what they're intended to do. So the fourth and final method is to use C++ 2023's new byte swap function. Yes, as far as C++ is concerned, they have finally got a standard method of doing byte swapping. You do need a very new compiler though. The version of Visual Studio that I have installed is too old. You can see here in my makefile, I'm saying we need the C++ 2023 standard. So yeah, I can do it with the GCC that I've installed though. And if you've got that, if you've got a compiler that's new enough, then you can include the bit header and you can use the byte swap function. And you don't need to worry about whether it's 1632 or 64-bit. It'll just do whatever needs to be done. And if you're from C++ 2020, there's also a way to check what the a standard way, finally, to check what the endianness is. Sadly, this is not available for C. Now, all of the example code I've shown so far isn't best practice for writing multi-platform software. And that's because I wanted to do the byte swapping regardless of whether the CPU is little-endian or big-endian. But in the real world, if you're writing multi-platform software that needs to work on multiple CPUs, you want big-endian numbers to be converted to little-endian on little machines. You don't want big-endian numbers converted on big-endian machines and vice versa. So on a big-endian machine, if there are numbers that need to be converted to and from little-endian, you want the conversion to happen, and you don't want that to happen on little-endian machines. So to do that, we can take the cue from the networking stack functions. So remember how the networking stack had H2NS and H2NL and whatnot, and they only did something on little-endian CPUs because network byte order is big-endian. Well, we can do the same thing. So it needs to be a bit of trickery to work around different compilers and systems doing different things. But then we create a whole bunch of, let me go down past the documentation area, create a whole bunch of CPU to big-endian 1632, 64, and big-endian to CPU. And then down here, CPU to little-endian and little-endian to CPU. So these functions say we are converting from CPU to big-endian format. And you'll see here, this code down here is for a little-endian CPU. So the little CPU to little-endian macros here don't do anything, but the big-endian ones do. And if we scroll up to our big-endian version of all of these macros, you'll see that the convert CPU to big-endian or big-endian to CPU, all of those macros do nothing. And the ones that convert to and from little-endian do. Now you might think, okay, this is a little bit redundant. You've got CPU to little-endian 16 and then little-endian to CPU 16, but they both do exactly the same thing. While that's true, having these, it's like self-documenting code. It tells you what the intent of the code is. So you know that right here, when you see CPU to little-endian 16, you know this code is converting from the CPU's byte order to little-endian. So the target is little-endian. And when you see LE to CPU, you know that the source data is little-endian and we're converting it back to the CPU. So it makes it, at a glance, you can see what the code's purpose is. And that's why we do it that way. All of the code that you've seen in this video is downloadable from Kia Campus for Creator and Elite tier members. So you can join the campus to get this and a whole lot more. I'll leave a link below the video. That's it for now. I will see you in the next video, which should appear over here.